Hi guys, it's Mrs. Milson. Okay, today we're going to talk about non-mutually exclusive events, okay? So these are events that can occur at the same time, okay? So non-mutually exclusive events are events that can occur at the same time, okay? So we're going to go about figuring out our probabilities a little differently than just writing out all possible outcomes and doing a probability model, which is what one of our strategies were for mutually exclusive events. Okay, so the two strategies we're going to tackle today are two-way tables and Venns. They kind of go hand in hand, and tree diagrams. Okay, and again, looking at our main note sheet, we're going to tackle this general addition rule, but we're going to talk about independent events and dependent events where either the and is given to you or we're going to calculate the and by multiplying the two probabilities together. Okay, we'll get to this one coming up. Okay, so again, all these still hold true, but we're going to expand on our general addition rule because now the and is no longer zero because we're not dealing with mutually exclusive events. We're dealing with events that can occur at the same time. Okay? So what's going to happen is we're going to have our general addition rule where the probability of event A or B would be the probability of A plus the probability of B minus the probability that A and B will occur at the same time. And since these are not mutually exclusive, this will have a value. You will either be given it for dependent events or we will calculate it with independent events, okay? So what we're going to see, we're going to do tables and Venns, we're going to do trees. So an and in a table is simply where the two events overlap. The and in a Venn diagram, again, is where the two events overlap. And an and in a tree is where we just go down a single branch that has the two events, and we'll multiply them. Okay, these will be independent. For the or part, okay, we can go through this process, but how it's going to look in the table, it's going to be all the cells for one event and all the cells for the other event. And you can see how you would subtract that overlap because it's occurring in both events, okay? Same thing with the Venn diagram. For the or, I'm just going to take everything in the two circles. And you can see if I have this whole circle and this whole circle, I have to subtract the overlap. I have to subtract the and because it's in both circles. Now the tree is a little bit more. We've got to multiply down several branches and add them up, but we'll do that one. Okay, so let's tackle our table and our Venn diagram with dependent events first, and then we'll do a tree with independent events. Okay, and I'll talk about independent and dependent. Okay, so the first thing we're going to tackle is a two-way table. Now this two-way table was created for us, okay, and so basically all the ands are given. So the probability of a student, randomly selected student liking chips and having a favorite color of red is 15 out of 200. The probability that a randomly selected student will like candy and their favorite color is yellow is 10 out of 200. So these are all the ands, okay? The ands are all the overlaps. Now, how do I know that favorite snack and favorite color are dependent, okay? How do I know these are dependent events, which simply means there's a relationship between the two? Well, I go back to chapter 1. Remember when we did conditional distributions? I'm going to do my conditional distribution by snack. So I have 15 out of 75, 16 out of 75, 12 out of 75, and 32 out of 75. So this is my distribution of colors by chips. This is my distribution of favorite colors by chocolate and by candy. And you'll notice that these distributions are different. And I even did a segmented bar graph. And we do remember that different equals dependent. Okay, so that's how I know that my events are dependent. Again, there's just a relationship. There's some sort of association between the two. Doesn't mean one causes the other. It just means there's a relationship. Going back to that, that's an important concept in statistics, seeing if variables and events have a relationship. Okay, all right, so I know that these are dependent. All right, so let's do a couple of our probabilities. So from my two-way table, okay, I can figure out the probability that someone likes chips is simply the total number of chips, 75, over the total number of people in the table, okay? So that's 0.375. Okay, so 75 over 200. And that's just a marginal distribution back from chapter 1. Okay, remember that back in the first chapter? Now let's do the probability that somebody has a favorite color of blue. Well, favorite color of blue, I'm going to come over here. So 60 out of 200. Okay, so 60 out of 200 is 0.3. Again, another marginal distribution. So now let's expand it a little further. Let's do our general addition rule. Well, first let's find the probability of and then we'll do or using our general addition rule. So if I do the probability that a randomly selected person likes chips and the color blue, the and is simply where those two columns intersect on the chart. So chips and blue intersect right here at 16. So this will be 16 out of 200. And 16 out of 200 is 0.08. Okay, so the and is always that intersecting cell. Okay, it's where chips and blue intersect. Okay, so now I have enough to do what's the probability that someone likes chips or the color blue. Okay, so again, going back to my general addition rule, I'm going to do the probability of chips plus the probability of blue minus the probability of chips and blue. Now, if these were mutually exclusive, that would be 0, but these are not mutually exclusive. A person can like chips and have a favorite color blue at the same time. So chips, I'm going to do these all out of 200. So 75 out of 200 plus 60 out of 200 minus 16 out of 200. So that ends up being 119 out of 200, which is a probability of 0.595. And if we look at our table, I'm taking all the chips, right? All the blue, so 75 plus 60, but I'm subtracting that 16 because 16 was in both totals. 16 was in the column and 16 was in the row, so I can't double count them. So that's why we subtract the and, because he was counted twice. So that gets my total. Now, of course, I could have added 15, 16, 12, 32, 36, and 8, and I would have gotten 119. Okay? So again, going back to this picture where the or is just all those cells added up. Okay? Now let's turn this into a Venn. Okay? So I'm going to put my Venn up here. Okay, now again, these aren't mutually exclusive, so my bubbles will overlap. So this will be chips, and this will be blue. Okay, and when you do a Venn, the easiest thing to do first is the and. So I know there's 16 people that like chips and the color blue. So I'm going to put them in the middle because that's my and. Okay. Let me move my table over a little bit. Light is creeping up on me. Okay. Now, this bubble right here in my Venn is all the chips. So this is all 75. Well, I've already got 16 accounted for. Okay. Oh, sorry guys, I'm knocking everything. So I know my total number of chips is 75, but I've already got 16 accounted for, so this has to be the other 59 chips. So now this chip Venn bubble is 75. 59 and 16 is the total 75 chips. Okay, now if I come over and do blue, this whole bubble has to equal 60 because there's 60 people that like the color blue, but I've already got 16 accounted for. So if I do 60 minus 16, that'll be 44. So there's 44 people that like blue but don't like chips. Okay, so this is how I would convert my table into a Venn. Now, if I think about this, what's the probability somebody likes chips? Well, I would have to add 59 and 16. Okay, so that would be 75 out of the 200. Don't forget the total 200. Okay. Probability somebody likes blue, I would have to add 16 and 44, which would be 60 out of the 200. Okay, and then my and is simply the overlap, the 16. Okay, and again, without this on the Venn or this in the table, I wouldn't have known that. So here, the and was given to me. Okay, now the or is going to be all of this colored in. It's going to be all of this, because if we look back here, the or is all the two bubbles. Okay, so if I take 59 plus 16 plus 44, I should get the 119, and indeed I do, okay? So in a Venn, I can just add up everything in all the bubbles, okay? Now, if this is out of 200, what's 200 minus 119? So there's 81 people out here that don't like chips and don't like the color blue. So all these numbers should add up to be 200, which is my total, okay? My total number of people. I personally like tables because this gives me a lot more information, because all this Venn is telling me about is chips in blue, and chips in the color blue. But my table is telling me about chips, chocolate, candy, and all 4 colors, okay? So this 81 can be chocolate, candy, blue, green, or red, green, and yellow. So this doesn't really tell me much about the other types of snack and the other colors. That's why I tend to like two-way tables a lot better. But you still should know how to do that, okay? So anyway, you can see the connection between Chapter 1 with dependent events, our marginal distributions. We'll get to conditional distributions in the next video probably, okay? I think in the next video. So this is an example of non-mutually exclusive, so the events can occur at the same time, and the events are dependent, which simply means there's a relationship between the two, okay? Now I gave you the Venn, I gave you the table. Not always going to give you the table. Let's do this one. Classes and hair color. We are told out of 50 people, 17 have blonde hair, 23 are juniors, and 6 are blonde and juniors. Okay, so it looks like we're going to use our strategy of creating a two-way table. And the two ways of the table are hair color and whether the person's junior or not, okay? So actually, it's really just blonde and juniors, okay? So if I think about my two-way table, my 2 are my 2 variables. So I'm going to have blonde and not blonde, okay? I'm not going to do blonde, brunette, redhead, because I don't know anything about brunette and redhead. I just know blonde and not blonde. And then I'm going to have juniors and not juniors, okay? I'll put not blonde. Because again, I don't know anything about freshmen, sophomore, and seniors, okay? So I'm just going to, there's going to be a little simpler table here. Okay, so this is my two-way table. My 2 are my 2 variables. Okay, so out of 50 people, so I know the total down here has got to be 50 people. 17 have blonde hair. So this is simply one variable, so that has to be a marginal. So 17 people have blonde hair, right? And so if I know 17 people have blonde hair and there's a total of 50 people, I know 33 have to not have blonde hair because these add up to be 50. Okay, so far I'm filling in my table. Then I'm told 23 are juniors. So here's my juniors, and again, this is a marginal, so my total juniors is 23. Well, if I know the total people is 50, then I know, what is that, 27 people are not juniors, okay? And then the other thing I'm told is my and. Okay, I'm told the overlap. So 6 are blonde and juniors. So blonde and juniors would be right here at this overlap. So that's 6. So now that I have this, I can fill in the rest of the table. So 23 minus 6 is 17. 17 minus 6 is 11. 27 minus 11 is what? 16, or 33 minus 17 should be 16. Everything should add up. Okay? So taking this information and putting it into a two-way table is going to allow me to be able to answer more information about the scenario. Okay? So, for example, if I asked you what's the probability that somebody is blonde, well, you didn't necessarily need the table for that because you know it's 17 out of 50, right? You know it's 17 out of 50. And then I can also do the probability that somebody is not blonde, which again, didn't necessarily need the table for that because I can just do the complement, 1 minus 17 out of 50, which would end up being 33 out of 50, okay? Now, what if I wanted to find the probability of, how about not blonde or not junior? Okay, so now this one, I might have to think through a little bit, and thank goodness I have the table. Okay, so not blonde or not junior. So again, if I think about my or statement, I can do the probability of not blonde plus the probability of not junior. Of course, I'm running out of room. Minus, totally running out of room, the probability of not blonde. I need another piece of paper. Let me get another piece of paper instead of squishing this. So this would be the probability of not blonde plus the probability of not junior minus the probability of not blonde and not junior. Okay, so if I think about my general addition rule, now this is where it might be helpful to figure out, or to have the table instead of just relying on the words. So probability of not blonde is 33 out of 50, right? Probability of not junior is 27 out of 50. And then not blonde and not junior is 16 out of 50, right? There's the overlap of not blonde and not junior. So now if I take those, let's see, 33 plus 27 minus 16. So that will be 44 out of 50, okay? So that, I think, is much easier to get from the table instead of just figuring out the words, okay? Because you could have figured out the not blonde from the blonde. You could have figured out the not junior from the junior, but figuring out the not blonde and the not junior, I don't know how I would have gotten it from that, okay? So organizing your information into a table is a great way to be able to answer more probability questions, okay? So again, not mutually exclusive, that and did exist, there was an overlap, okay? And it was a lot easier to see when you create a table, okay? Now, I'm assuming these events are dependent, okay? I can check my distributions real quick. So 6 out of 17 and 11 out of 17. And then 17 out of 33 and 16 out of 33. Well, 35% and 51% are not the same, and 64 and 48. So these are also dependent. There is some sort of relationship here between hair color and class, okay, whether you're blonde and junior, okay? And again, the and was given to you, okay? An and was given to you. So back to our main note sheet, when A and B are dependent events, you're either going to be given your and, okay? Your and is going to be given to you, and we'll deal with that in a second. Now let's talk about independent events, okay? Because we're going to have to calculate the and. Okay, let's look at some independent events. Now, the best independent event I can always think of is flipping a coin and rolling a 6-sided die. There's no relationship between flipping a coin and rolling a dice, okay? They don't impact each other, okay? They're independent events, okay? So what I'm going to do is I'm going to create a tree, okay? So when I flip a coin, my only options are heads or tails, right? And when I roll a die, I'm going to get any number between 1 and 6. Okay, so I'm going to create a tree first. So I'm going to flip my coin first. Okay, and I tend to do trees. I tend to do trees when I have a sequence of events. Okay, so sorry guys, let me move my table again. The light is creeping up on me. Okay. You know, the snacks and hair and favorite color, that wasn't a sequence of events. You just asked the person 2 questions, okay? So I'm going to flip a coin, and I'm either going to get heads or tails, right? And I know there is a 0.5 probability of getting either one, okay? And then I'm going to roll a die. So each die, 2, 3, 4, I have 6 possibilities. I'm either going to get a 1, 2, 3, 4, 5, and 6. And each one of these has a probability of 1/6, of happening as 1/6. Okay, and same thing down here. 1, 2, 3, 4, 5, 6. Okay, and again, same probability if it's a fair die of occurring is 1/6. Okay, now now again, these are independent events. Okay, now in independent events, the probability of A and B is simply the probability of A times the probability of B. And I want you to understand why, okay, because it's coming from a tree. Now, if I write out all my possible outcomes, I have, let's see, I have heads 1, heads 2, heads 3, heads 4, heads 5, and heads 6. Or I could get tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. So I know I have 12 possible outcomes. Okay, so if I want to do the probability of getting a heads, okay, well, the probability of getting a heads is simply 0.5, okay, when I flip a coin, independent, okay. Now, I'll talk about that in a second. What's the probability of getting a 3, okay? Now, the probability of getting a 3 is going to be down this branch and down this branch, okay? But I can also look at it here for my possible outcomes. These are the only times I'm going to get a 3, okay? So this would be 2 out of 12, okay, or 1/6, which is, I don't know what that decimal is, which is 0.17, okay? Now let's look at the heads from this also. Probability of getting a heads is 6 out of the 12. Okay, let me write that down. So 6 out of 12 is also 0.5, okay? So if I look at all my possible outcomes. Now what about the probability of getting a heads and a 3? Well, the probability of getting a heads and a 3 is only right here. So it's really just 1 out of 12, okay? Now if you look at it from the branch of a tree, it's just simply this branch right here, a heads and a 3. So if I take 0.5 and multiply it by 1/6, okay, so that's 1/2 times 1/6, that's also 1/12, okay? So when you're given independent events and you're not gonna be given the and, you can simply find the and by multiplying the two probabilities of each individual event together, okay? So if I took probability of heads times the probability of 3, I would take 0.5 times 0.17, 0.5 times 0.17, and I'd get 0.085, which is roughly 1/12, because I rounded that one, okay? So I should really take 6/12. I should have done 6/12 times 2/12. 6/12 times 2/12, which is again my 0.083, okay? We're not gonna use that one because we rounded the 0.7, okay? And that is 1/12, okay? Now the only time, it's good to assume all events are dependent unless you're told they're independent, okay? Let's finish this off by doing an or. Let's do the probability of a heads or a 3. So I know I just have to take the probability of heads plus the probability of 3 minus the probability of heads and 3. So the probability of heads is 6/12. Probability of 3 is 2/12. And then I have to subtract the probability of heads and 3, so that's 1/12. So that'll end up being 7/12, okay? So if you think about that, heads or a 3 would be heads or a 3, and that indeed is 7/12. Don't know what that is in a decimal. 0.58, okay? So these are independent events. So again, when you are given independent events, it's still, where's my paper? It's still the same general addition rule, but in order to figure out the and, you simply have to multiply the two events together, okay? You won't be given the and, but you will be given the probability of the two events, or you'll be able to figure them out. We knew the probability of flipping a coin and rolling a 6 die, okay? But this or general addition rule still stands true. The and is just a little different, okay? Before I finish this, we have pretty much touched on almost all of this except for the conditional. We've done every single type of strategy. It all boils down to this general addition rule, okay? And the devil is in the details of the and. If the and is mutually exclusive, if the events are mutually exclusive, and is 0. If the events are dependent, you're usually given and, okay? And we'll talk about conditions in a second. And if the events are independent, you can calculate the and, okay? So adding them up is always the easy part. It's figuring out what you've got to work with the and. Are the events mutually exclusive? Are they dependent? Was the and given to me? Or are they independent that I've got to calculate the and, okay? And I can use these strategies to organize myself, okay? All right, I hope this was helpful, and I will see you all next time.